Hello everyone and welcome back. What if engineers could predict these dangerous vibrations before a bridge is ever built? In this video, I'm going to show you exactly how engineers use ANSYS Workbench to identify the natural frequencies and vibration mode of a bridge. By the end of this tutorial, you will know how to perform a complete modal analysis and understand one of the key reasons why bridges can fail. And make sure to stay until the end because we will visualize the bridge most dangerous vibration mode and discuss how engineers prevent these failures in real-world structures. So, every structure has a natural frequencies, and think about like a guitar string, for example. When like pluck it vibrates at specific frequencies. Bridges behave the same way, just on a much larger scale. If external forces such as wind, traffic, machinery, or even pedestrian match one of these natural frequencies, resonance can occur. So during resonance, vibration amplitude like increase dramatically, potentially like causing fatigue damage, discomfort, or even structural failure. That's why modal analysis is one of the first simulation engineers performed during the design phase. Today we will use this like bridge model to find the natural frequencies, mode shapes, and critical vibration patterns. So let's get started. First of all, I'm gonna stop this movement here for this beautiful bridge and go back to the workbench so we can perform the same analysis together and learn this along on this video. As you can see, first of all, in order to perform a modal analysis, you have to take this modal analysis from the toolbox and put it on the project schematic. And after that, we open the geometry. I usually prefer to use space claim. You can use another modeler like design modeler or discovery. In this tutorial, I'm gonna open it with a space claim. So right click and you click on the open space claim. I already open it, so I'm gonna open it right now directly. As you can see now, I opened space claim. On the first time you will have a blank screen, so you have to import the models. For that, I will put you on the description down the link to download this CAD file of this steel bridge, so you can practice with me along in this video. So actually, after importing the geometry, what you have to do is to do a global check of the model to see if you have any missing spots or you have anything to be fixed and so on. First of all, I recommend you always to go to prepare and click on interference to see if you have any parts that they are over each other, and it seems on our structure it's clean, as you can see. And now actually I'm already know that I will define the boundary conditions later on, so I did already actually split the bottom face. As you can see, this bottom face I did split these 4 small faces at the corners in order to put my fixed support only at this corner and not on the overall face, just to make this realistically as much as possible. In order to make this splits, all what you have to do from design, you click on split, you choose your face and split it at the place that you want. After we finish preparing the model, we are now ready to import it to the mechanical environment. So now, before go into the mechanical environments, actually let's define the material, which is very important, especially in modal analysis. So for this example, actually, I'm gonna open the engineering data. I'm gonna actually use here a structural steel, as it is always defined by default in ANSYS. And the most important properties for a modal analysis are 3 main things, which they are the Young's modulus, the density, and the Poisson ratio. Density is especially critical because natural frequencies depend on both stiffness and mass. A heavier bridge generally like vibrate at lower frequencies. Once the material like is assigned, we move like to the mechanical environment. So I'm gonna close the engineering data and I'm gonna directly open the mechanical environment. As you can see, by opening it, like it will take some time, so your model will be like imported to this environments. And now we have to create the mesh. So the mesh will divide the bridge into like thousands of small elements used like for numerical calculations. And for a quick study, we will use an automatic mesh, but not like generate, just click on the mesh and generate. So actually I am gonna like to change the element order from linear to quadratic, and I'm gonna give like an element size of 2 millimeter. Now actually you have like two ways to generate the mesh. You can like mesh it like as once by clicking right click on the mesh and generate mesh. On such like models where you have like a lot of parts, it's recommended to like mesh it like by groups. So how to do this? I'm gonna first to change the selection from the surface to bodies and the mode from single to box. So first of all, I'm gonna choose actually the upper area of my bridge and hit generate on selected bodies. I will wait a little bit until he's finished and move to the other like section. So as you can see, he did this like so fast. Now let's mark the middle area and generate selected bodies. And finally, you can like always like see what he do actually by clicking on the mesh down. But for now he's done, so I'm clicking the final stage down, which is generate on the selected body. And so now as you can see it's finished, and I have a green light like near to mesh, which is mean like I already meshed all the model that I have. And like as you can see, like and now like we notice how the structure like is discretized like into fine elements. And remember, like a finer mesh generally improves accuracy but increases computational time. So for professional engineering work, always perform a mesh conversions study, which is like you can make the model, you can make this study on this like current mesh with this current element size, and you can do it again with a smaller element size and check the results or compare them and see if the mesh were like responsible to changing the accuracy of the results. So for this tutorial, our mesh is sufficient to understand the model behavior. Now we need to represent how the bridge is like connected to the ground, and this step is extremely important. If boundary conditions are incorrect, the model results will be like meaningless. So I will apply fixed support at the bridge like foundations, in specific the four corners that I already defined before. So as you can see, I already like have these like corner faces. I did like here defined a fixed support on each one of them, on all of these faces, as you can see. So I have fixed support on all these faces. Depending on your model and on how much realistic you wanna like to define this, you define the boundary condition. So now actually like these supports like prevent movement at the connection point and like represent the structural constraint at the end. So I'll always verify that your support conditions reflect the real world structure as closely as possible. That's very important. So once the support are applied, we are now ready for the model setup. So for the model setup, like we can like check it by clicking on the analysis settings, and here we define actually the number of modes to extract, which is like named in ANSYS under the max modes to find. For this example, I will request the first 6 modes. So why 6 actually? Because the lower modes usually dominate structural behavior and contain the most important dynamic information. So the solver will now like calculate natural frequencies and corresponding mode shapes. These frequencies like represent the structure's preferred vibration patterns. So after you finish the setup, now you are ready like to hit solve by clicking on solution and solve the model. So I already solved the model for you just to save time and go directly to the result. As you can see, we have this model. And after you finish by clicking on solutions, you will get on the table to the right like the 6 mode shapes that we requested or asked him to find. And in order to see the mode shapes, all what you have to do to select all of them and right click and create mode shape results. After that, you go to solution and click on the evaluate all results. So you can like request the solution and see every mode shape. So now we can examine the results. Let's look at mode shape 1 and hit like play just to see it like how it moves. And this is like the bridge like first natural frequency, and like notice how the entire structure like bends in a global motion. Now let's examine the second mode shape and hit play. So here we see like a different deformation pattern. And as we move actually to higher mode, the vibration shapes like become more complex actually. So this is like where modal analysis becomes actually powerful. So like we can like check them, all of them, like the third one, as you can see, we'll move from the bottom. The fourth one is like become like now really complex, the behavior. And we have this mode shape and the final one there, or the sixth like mode shape like this. So the frequencies actually, as we have there, like in hertz, like them themselves like are important, but the mode shapes like tell us exactly how the structure like wants to move. So if a loading source excites one of these frequencies, the corresponding mode can become like highly amplified. So let's compare all 6 modes, like we like already like saw all of them actually, from the less complexity to the complex ones on the end, like the 4th, 5th and 6th mode shapes. And we notice like how each mode like reveals a unique vibration pattern. And this pattern helps engineer to identify weak areas and potential resonance risks. So now let's like connect this analysis like to a real engineering disaster, which is the Tacoma Narrows Bridge collapse is often like associated with resonance and ioelastic effects caused by wind. So the bridge experienced like oscillation that matches critical dynamic behavior of the structure that we have. So as vibration amplitude like increased, the bridge entered like an unstable condition and ultimately failed. So model engineer like use advanced dynamic simulations, including modal analysis like we did like today, and as an essential step to avoid like similar failures. So while modal analysis alone doesn't predict collapse, it provides the foundation for understanding how a structure responds dynamically. So today we learned why bridges like vibrate, what natural frequencies are, which we got like on this table, and how to perform a modal analysis in ANSYS Workbench, and how engineers identify potentially like dangerous vibration modes by looking into each one of these mode shapes and looking at the critical locations and try to improve these locations. So, and now you can see like that the bridge failures aren't always like caused by excessive loads. Sometimes the biggest threat is a vibration frequency hidden like inside the structure itself. So if you found this video helpful, leave a like and subscribe to that channel. So thanks for watching, and I will see you in the next video.